Okay, hello everyone. Thank you very much, Mathilde, for inviting me. So I thought, when I saw the title of the workshop, maybe I don't want to talk about teas today. So I tried to step back and think about how I could basically deal with creativity, innovation, and exaptation, but stepping back and thinking at our general scientific approach. So this is totally exploratory and maybe will seem too basic for you, but these are some thoughts I gathered over the last few days. So basically, we every day handle theories, methods, and data. And because we have a fragmentary fossil record, this, of course, is challenging our scientific creativity and innovation. And of course, we have a good deal of failure, which will always stimulate our motivation, our creativity as well. So first, I started to wonder, but what is the real difference between creativity and innovation? Because I am not familiar with this vocabulary in my own research. So I found interesting that these authors listed a couple of arguments to make a clear distinction between the two concepts. Creativity is more about generating ideas, while innovation is more putting the ideas into practice and making it happen, basically. So there is a notion of considering benefits of the creation of the ideas that the creativity came up with, and that's what we have seen as well with the talks by Francesco, by Luc, talks about cultural material. And creativity is often like the spark we talked about this morning about an individual idea, and the innovation might better be within group or an inter-individual realization of that idea. Creativity is an absolute novelty, but it doesn't mean it will come into something concrete, as Francesco explained, whereas innovation is usually novel, but not necessarily, and it will come to something actually concrete that will be used. Originality is really important for creativity, while innovation, it's about effectiveness. So it means, for example, if we go back to the talks on tools, if the tool is a new idea but that it's not effective or that it's breaking at the first use, the idea won't be retained, and the chaîne opératoire to produce the tool won't be like set in stone as something to keep in the culture. And sorry if my vocabulary is not precise, Francesco. I try to step on fields that are not mine for once. So creativity is more about reflection, as I said, sorry, and innovation is more about action and contact with reality and also with raw material. I want to step back 1 second. So at the CNRS, we had a survey about quality of life at work. And basically, we had a set of questions that was from the INE, so one of the institutes of the CNRS, and asked the question to researcher, why do I do the job? Why am I happy to do the job? And the answers were 3. And the result of this survey revealed that basically by passion we do this work, yes, certainly, scientific freedom, transmission of knowledge, but also creativity. And I found that really interesting because that's the stimulation of emitting new ideas that is motivating really researchers. And I was then surprised not to find the word innovation. But I understand that maybe, as I thought before diving into these subtleties of terminology, most of people maybe see creativity and innovation as interchangeable and don't see a final difference. So this is obviously a key skill we need to have for our profession. So what about exaptation from a methodological point of view? I thought, I'm stuck there. So coming back to a rough definition, exaptation is a discontinuous evolutionary process, as we saw this morning. For example, you may have some phases of stasis and then some phases of more rapid progress, if I may say, in the invention. And it's basically a shift in function of an already existing trait, feature, or an artifact. And so far, it's mostly restrained to evolutionary biology and not so much in other fields. Yet, we can apply it, I think, to a lot of other methodological fields because it's a way of trying to find a new way, a new method to resolve problems that have been long-standing and for which we need really to go somewhere else, basically to call for interdisciplinarity to solve that problem. So I took an example, finite element analysis, which is basically some applied mathematics where you will model an object and test the material resistance of that object under some pressure or some loads, under a mechanical scenario, basically. So the idea is that a complex object is discretized into finite elements, so cubes, tetrahedra, whatever, and then each element is attributed a material property. Then you apply a force, and then according to the response of the material, you see what happens. Does the material resist or crack? So this was mostly, I would say, like in purely material sciences, but then in biology, we have started to apply these techniques. So I remember a paper by Rayfield in 2007 applying it to dinosaur skulls to test basically how the morphology would be adapted to catch prey, or even the musculoskeletal apparatus, would it be like well adapted or not for the dietary regime we would interpret for this specimen of dinosaur. More routinely, for example, in orthodontics, one would make such simulation, for example, to say, or if you have a dental device, like some brackets or so, if you apply some loads by basically putting it super tight with a wire, like what will happen to your tooth? So this is the tooth root that was modeled here, and basically the conclusion is that if the forces you apply are too high, you will have a root resorption. So basically, if the forces are not well distributed, you may end up with a big problem that your roots are going to resolve. And I heard about the case of a young lady, 15-year-old, where the orthodontic treatment was not properly designed, and she had a general root resorption of all her teeth. So basically, at 15-year-old, she was losing her teeth, and she had to get implants. So this has really serious influence on the way we interpret morphology, and also the way we understand the biology of hard tissues. So for me, this is a case of methodological exaptation. So innovation and creativity also enable us to challenge what I call well-established theories. So for example, we see some patterns in terms of morphology, biology that are recurrent in various taxa. And we spend a lot of time trying to explain them by using functional adaptation, development, dietary adaptation, but yet sometimes they still remain unanswered. So for example, this is a virtual section in a wisdom tooth of a Miocene monkey, so Anapithecus erniaki, that I studied at the synchrotron in Grenoble. And so to make it simple, here you have the tooth crown with the enamel and the underlying dentin. And you may guess some really fine growth lines in the enamel and the dentin, and you see you have more accentuated lines, they are darker. And the big story in the moment in dental anthropology is understand what are they? Can we call them stress? And are they related, for example, to a dietary shift, a disease, a psychological shock, like fever, malnutrition? It's really a big dilemma because stress in dental tissue are non-specific. So it means you may see a lot of stress, but you may not get the answer about what caused them. So this is by studying the microstructure of teeth, but you can use other techniques such as biochemical analysis or elemental mapping to try to have an idea. For example, do you have a variation in calcium, in strontium, in zinc? And then this may tell you about what happened in the physiology of the individual. Yet, even if you get such a signal, you may still remain with your question mark because the physiology at such a fine level is still not well mastered. So that's where, in my opinion, to challenge this well-established theories that sometimes are passed upon generations of researchers, interdisciplinarity and methodological development are key so that we don't stay always in the same highway of thinking, but enable or allow ourselves to look also on the side to reappraise this research and have new ideas and potentially deconstruct methods. This may even cause the fact that we have more questions than when we started, and that basically we have to look for even more evidence. And this will in return, of course, stimulate our own creativity to solve these new problems. And I want to show you one. I said I will not show too many teeth, that's the last one, I think. So when we study dental development, there is a key event when we want to calculate the age at death of a specimen, it's birth. It's our time zero. And birth is recorded in dental tissue, especially in the milk teeth, the deciduous teeth, as a special line that we call the neonatal line. You can see it here. It's in a molar from a kid. And you see here the root is missing, and it's normal. It's because it got resolved because the kid just shed his tooth normally, as we all did in our childhood. So when you see this, this neonatal line under the microscope, the traditional explanation is, oh yes, it's a decalcified area of the enamel, so it's an area where you have less calcium, and it's related to the physiology, the stress of birth, you know, with the equilibrium basically between the mother and the infant. Fine. But the problem is that when you look, so still under the microscope you see it well here, when you look at it with a synchrotron X-ray fluorescence to do an elemental mapping, and when you look at the calcium map, you would expect to see a big black line because it's depleted in calcium. The problem is that here we have a specimen where it's barely visible, and it's not the only one. We have several specimens with modern humans where basically you barely see the calcium. And this is really a big problem for us because this was like the common gold standard explanation of what is a neonatal line in primate or vertebrate enamel, that it's a decalcification. I just put the maps of strontium and zinc to show that in other elements it's better visible, and that's related to the physiology and the stress of birth, but I don't go in detail with this. Then we have the problem of missing data. How do we deal with missing data or with our fragmentary fossil record? So fossil data, missing data, are a permanent state. We cannot recover them, but we still have to work with what we have. So they limit our interpretation, our theory, and also the way we can collect data. So in recent years, several types of statistical analysis have been developed to try to estimate them, to make models, to try to compensate for their absence. And for example, in genetics, or we see later in geometric morphometrics, this has been really powerful to try to go further in our models. So I quote here one of our colleagues from PACEA, geneticist Melanie Privot, who did a presentation last week at the scientific meeting, and that was talking about creating missing data. So that may sound funny. We wouldn't write that in a paper, but this is somehow true, and I will show what basically she explained. So this is a site, Burgi, where basically you have a cemetery with some burials, and basically our colleague geneticists together with archaeologists were able to reconstruct like a full genealogical tree with all the kinship, basically, relationship between individuals. And what I found fascinating in a way is that they can tell about individuals for which we have recovered no bone, not a piece of tooth, nothing. But just by inferring or by the way genetic data analysis works, you know that, for example, this individual had to have a grandma, otherwise you couldn't basically extract the DNA of the grandma from which you find a bone. This may sound a bit silly, but I find it fascinating that all the data is really entrapped in the DNA, and so thus you can really recover the full story. It's a bit the same story with when we work with 3D models, basically. So again, fragmented missing parts and distorted specimens. So here it's the Turkana boy. And a lot of methodological tools have been developed. For example, using mirror imaging for basically completing some missing parts, assuming thus that symmetry is a valid concept in this specimen, and then using more elaborate techniques to evaluate, even missing parts that have no symmetric contralateral. So I think all this mathematical development have been stimulated, especially by the fact that we cannot satisfy ourselves with the pure material evidence we have. We are always tempted to basically try to interpret the whole object, the whole story, to be able to tell more about it. And I think that's about it.